So this is a lecture that historically has gone on exam 2. It didn't go on exam 2. By the way, I have no idea. The mean was 69. I know part of the reason it was lower than the last one, but I thought the mean was going to be 85. I thought everyone was going to be out of here 20 minutes before the end of the hour. I don't know what happened. Any insight would be appreciated. I've got a couple people that have come to me already, and I'm saying to them, you know, go through the exam. For ones you missed, tell me why you missed it. And I need to figure this out, because 5 of us went over this exam, and we all thought it was going to be easy. So. Okay, so now back to this. And, you know, 30% of the class is still going to end up with an A, maybe more. But, you know, that's a separate issue. I want to know why this didn't go the way I thought it was going to go. So here is the theme. How data are presented can affect interpretation. That's what we're on about. And I got a few examples that we can look at. Okay, so this is a figure out here chapter. It's actually revised from what was up there at the beginning of the semester. These are hypothetical data. So I'm imagining we're counting number of people at a rally. For candidate 1 on the left, candidate 2. Which graph gives the most favorable impression of candidate 2's popularity? It's not a trick question. The top one. Which gives the least favorable? Okay? All 3 graphs present exactly the same data. So, and of course, you might actually be able to see that if I had a way of blowing this up. It has to do with the scale. So the bottom one is the most accurate, or the most legitimate, I guess I would say. They're all equally accurate. The top one has, so the scale here goes from 0 to 1500. Here I started the scale at 500, right, which sort of cuts the graph off here and creates the impression of a bigger difference between the two than there is. Anyone want to take a guess on what I've done in the middle one? A what? It's not broken, but there's a transformation that you can use, which is actually useful in many contexts. So what kind of scale? It's a log scale. To take logarithms and numbers, and suddenly big differences shrink to be much smaller. Okay, so that's point 1. Oh, I do have another example of that. Scale of presentation in a graph matters for visual impression. Those I made up. These are not. This is now I guess about 10 years old newspaper in Idaho. Has to do with steelhead. Steelhead are what? Fish. Good. What kind of fish? Salmon. Trout and salmon are pretty much the same. So up in the Northwest, there's a conflict between wildlife in the water and dams, right? And these fish, this is biology, so you can just completely shut this out. But the salmon are born up in fresh waters, and then when they get a little bit older than born. They swim out to the ocean, they grow up there, and then they swim back to lay eggs and dump sperm. And the dams get in the way of this, and so there's pressure up there. You know, the dams provide electric power, and so there's a real need for them up there for, you know, society. And the concern is, you know, are these salmon all going extinct because of the dams, and do we need to blow up some of the dams and let the water run through? So one of the things the fisheries people do is they count fish returning across the dams, right? And they've built fish ladders and things like that. And so this is a record now of from 99, so I guess it's just spanning 4 years, at 9 different dams. And the blue represents the number of fish observed coming back. And the red line is the average over the 4 years. So what is the first impression, just visually looking at this across the 9 graphs, what one thing jumps out? I don't know. You're asking me a biology question. Why would I know that? You know, it could have to do with the amount of rainfall they received. I don't know. Maybe they had more people hired counting fish. I mean, well, I said that jokingly, but those are the sorts of things you have to pay attention to. But so you look at this, and what's the overall impression about all 9 dams? The what? They're not the same, but they look like they almost are the same, right? I mean, they're all in the same ballpark. It's like, okay, well, they're all about the same. And that's probably what most readers thought. Then you look at the scale. That helps too. This graph goes to 1,000, and this, by the way, is in thousands of fish, so that'd be 1,000,000, right? Well, this goes to 500. We get down here, we got one that goes to 50. We got, you know, several that go to 100. So the ones that go to 100, on this graph, the whole graph in the lower right corner would fit in this part of this graph, right? That little itty bit is where this whole graph belongs. And so, you know, you look at this, you think, yeah, well, they all look like they're doing okay. And of course, they put the one with the highest scale up in the left-hand corner, which is the one where your eye's first going to go to. So here's a real example of what I was just talking about. And you know, they could have done it differently. How many are not ready to text in but think they will in a few minutes? I'm overwhelmed. Okay, so I got to tell you something. There's a form at the top that says questionnaire X, questionnaire Y. Now, go ahead. If you're done, talk, look at your phone, I don't care. I'll give you a couple minutes. And you can work on question 2 as well if you're done with question 1. What?
He hasn't started.
So deal with question 1 first. It's not tricky. And if you have questionnaire X, answer here, and then we'll do Y next. Okay, now if you have form Y, do the same thing. Okay, well that distribution looks a little different than the last one. So here's what the numbers look like. We had 11, 15, and 13. So pretty even across there on Form X, but we had 2, 4, and 20 on Form Y. So we have a difference here. Let's look at what the difference is. Questionnaire X reads as follows. They both read the same initially. You are told about a drug that reduces heart attack risk for people in the age group of your parents. It costs $5 grand a year. How likely are you to recommend it to your parents if it reduces heart attack deaths by 50% per year? Questionnaire Y presents the same information, actually presents it a little, perhaps one additional statistic, reads the same, up to how likely are you to recommend it to your parents if it reduces heart attack deaths from 2 in 100,000 to 1 in 100,000 per year. That's a 50% reduction, right? The two mean the same thing. The first description doesn't tell you what the overall risk is. It just says whatever the risk is, it's reduced by 50%. Which manner of presentation you think the drug companies prefer? The first one, which is a presentation of relative risks. So the point here is data on risks can be presented in relative versus absolute terms. Relative is usually more impressive than absolute. And we can put, at least from a drug company perspective. Okay, next question on your questionnaire. If you have Form X, this is a question about if you get a test result back that says you're infected with something, what is the chance you really are infected? So Form X first, please. If you have Form X and you're not texting in, how many are choosing A, B, C, yeah, okay, well, I'll say 1.5. D, E, F. Okay, so we have oops. Right, okay, go to form C, form Y. Hello. Okay, if you have form Y and you're not texting in, how many are choosing A? B, C, D, E, F. Okay, we see a substantial difference between the two. Certainly not universal, but we didn't see this big pulse last time. Let's look at what these mean. Questionnaire X. So has to do with false positive rates for any kind of test you want. We want to know the chance you actually have HIV given a positive test result. You're given the following averages for people in your age and risk group. 1% of them are infected, 99% are not infected, right? That stands by itself. 95% is the chance of testing positive if you are infected by HIV. 2% is the chance of testing positive if you are not infected with HIV. Put these together and you think, well, if a positive result comes back, right, and there's no other information, it's like, what's the chance? It doesn't seem very likely that a positive result would come back and you're not infected. Here are the same data presented a different way. On average, for 100 people in your age risk group, the following statistics apply. On average, one is infected, right? That's the 1%. And there's a 95% chance they will test positive. In other words, that one person will almost always test positive. 99 are not infected, but because there's a 2% error rate, 2 of them are going to test positive anyway. So now you're asking the question, well, out of 100 people, what fraction of the time does a positive result really mean they're infected? It turns into 1/3. They're exactly the same data, but one is vastly easier to mentally keep track of than the other one. There's a guy, Gerd Gigerenzer, I think is his name, wrote a book on essentially this problem, right? It's not a big book, but on this problem. He's given surveys to physicians. Physicians don't know how to do the calculation, right? They think it's, if you get a positive result back, it's very likely to indicate infection, but it's not, right? The issue, and the way you can sort of sort this out in your head is following. Suppose no one in your risk group was infected. You get a positive result back, you know it doesn't indicate that you're infected, right? So the problem here is you got overwhelming numbers of people that are not infected, should not test positive, but even if you have a low error rate of the test, that means that several individuals are going to come back with positive results. So that's what's sort of leading to this apparent paradox here, that you can have a test that's really accurate, but most of the positive results you see will not indicate infection. Oh, I just made it up. I mean, it is low, but it's in the ballpark, but you could have made it 3% or anything like that. Yeah, the 2%, I mean, this I'm just making up the numbers. The false positive error rates are low, but I don't know if 2% is accurate. And it's going to vary from test to test, and it's probably going to vary from time to time. You know, the lab gets in a new batch of testing kits, and that error rate's going to change.
Can you explain that 1 again?
Okay, so what we're really asking here is, of all the tests that come back positive, what fraction of the time is the person really infected? So what you're looking at is, so the denominator here is going to be the number of all positives, which includes true positives and false positives. That is 1 plus 2 here. We're saying out of 100 on average. Okay, well, of the true, so these add up to 3 out of 100. What fraction of those really were infected? Just 1. Well, sorry, no, how many of those 3 were infected? It's 1. So that is the rate of true positives given a test result that says you're positive.
So it's the amount that are actually positive over the amount that came back.
Right. So I'm not asking you to do the calculation, but I'm asking you to see that there's an easy way to present the numbers and a challenging way to present the numbers. That's what this lecture is about. You're interested in getting this lecture moving on, aren't you? Do we want to dwell on this anymore? I mean, this actually could be practical, right? You're going to be subjected to lots of tests, and you know, some of them are going to come back positive, not necessarily for you individually, but for this class as a whole. And a lot of those results are going to be bogus. And if you're in a position where you can actually mentally calculate, figure out what's going on, you may be a lot better off, right? There are cases in this book that I was talking about, describes cases of people that got results back saying they were infected with HIV, and it's like, well, if I'm infected, then I'm going to go out and have a good time. And, you know, they come back a couple of months later and find out, oh, no, you're really not infected. So there is some practical value in this particular one. Right, and so if you get a positive result and you think, oh, you know, this is like the end of my life, step 1 is to be retested. Always retest. There's a guy at Rich Siegel at whatever it's called, Southeast Louisiana University, and he said his wife worked in some blood clinic, and they test them for HIV. I mean, she's like a nurse that sticks needles and such, and she came back with a positive test, and he said, you know, we didn't think anything of it, and she just went and got tested again, and yeah, she came back negative the second time. So be aware that if a test can be highly accurate, but a positive result can still usually mean that it's a false positive. Okay, the last thing on here hasn't worked. It's kind of bogus, but I'll tell you what the point was. the scale used to present or provide choices can influence the choice. In particular, if we are clueless about what the choice should be, and there's a range of numbers there, what do you think people do? What? Yeah, they go for the middle. Whatever the range is, if you haven't a clue, people tend to, they aren't going to pick the extremes. They choose for the middle. And that's not saying exactly in the middle, but away from the edges. And the last point is summaries versus the raw data. So even in my field, we rarely see the raw data anymore. We're seeing summaries and such, and especially in medical research, right? You'll read things in a newspaper, you'll read things, even if you go to the extent of reading something in JAMA, Journal of American Medical Association, physicians and that, they're not looking at the raw data. They're reading summaries, they're reading distillations, abstracts, and so on. Oh, yeah, I'm going to have to put number 3 down, won't I? Okay. I'll put it down when we get done here. Thank you. So almost everything we are exposed to is some form of data summary. Summaries provide an opportunity to change the emphasis. And this happens in medical research, right? A study will get done, and then whoever has a vested interest, will commission someone to write a summary of it. The summary can be really detailed, but the emphasis can totally change. So 3 up there. Data presented as what's called conditional probabilities are more difficult to comprehend than data presented as simple averages. So as I say, the emphasis here is not you doing the calculation, it's understanding that there's a difference in, there's an effect of the way we present data. And if this ends up on, which probably will on the next exam, I will give you more insight as to what I expect from you. In the meantime, get out of here.